Hello, you absolute legends. On a titration curve of a weak acid and a strong base, a second point that we're going to look at is what's called the half equivalence point. If you're looking at a titration curve raw, you would kind of try to predict or eyeball the straight line segment here and try to guess what the middle is right here. And that would be the half equivalence point. At the half equivalence point, we know that the moles of acid is double what the moles of base are. So we say there's half amount of moles of base, so it's the half equivalence point. At the half equivalence point, this atomic vision picture shows that half of the acid has reacted with the base, and the other half of the acid remains unreacted with the base. If this half has, whatever the moles of base, the moles of acid you started with, half of it has reacted, half of it hasn't reacted. So these values here are going to be very similar, if not identical to each other. At the half equivalence point, we use the Henderson-Hasselbalch equation because the math works out very nicely and logically. No rice table needed. We logic and reason through this. Half of the acid has reacted and the other half isn't. So whatever these numbers are, they are going to be identical because half did it, half did it, half didn't do it. So this number is going to be this fraction equals 1, log of 1. This drops out. So we have a value here where pKa equals the pH. Two ways you can run this, two ways this question will be asked to you about a half equivalence point. One question could be, what is the pKa? Asking you to calculate the pKa. In that case, you'd be given the pH. You would eyeball the pH off of a titration curve. You know, just look up and say, okay, that's the pH value right there, whatever's on the y-axis. The other way this question would be asked is kind of a flip-flop. Here's the pKa of a known acid. What should the pH be? And this question could be asked in an idea of like kind of a theoretical, like a planning situation here. So if you're given the pKa, for example, the Ka for acetic acid is a known number. It's a small number. This is a K value for a very specific weak acid that I'm using only as an example. This is a number I know. I can punch this into my calculator and solve for the pH. The vice versa way. You measure the pH. You run the titration curve and you don't know what the acid is, but nevertheless you run the titration curve and you calculate and you observe a pH of say 4.74. I am just making this number up for illustrative purposes. Over here, you can solve for the Ka by getting the unknown, like getting rid of the negative sign or moving it over to the other side of the equation, doing the inverse log. These are log base 10s. So that is how you isolate that and solve for the Ka value. And the Ka value is a known physical constant about an acid. It is very similar in style to like thinking about the density or the melting point of something. Like These are known physical constants. They're referenceable, they're Googleable. With a half equivalence point, we have a unique situation where half of the acid has reacted and half of it hasn't reacted. So this log term drops out. Math looks clean with a little bit of log stuff. I hope this helps. Thank you.